This is section 7.1 continued. I am on page 3 of our notes. Top of the page, it says requirements to create a confidence interval for estimating a population proportion P. There's 3 things there. We're going to go ahead and give that a star. We have, first thing, sample is a simple random sample. 2, conditions for the binomial distribution are satisfied. That's in section 5.2. There's 4 things that you would have to verify, so you should go back and know those. 3, verify the normal distribution is a suitable approximation to the binomial distribution by verifying both n times p has to be greater than or equal to 5 and n times q is greater than or equal to 5. The higher level of confidence leads to a wider interval and a larger margin of error, and that has a bunch of stars. We'll underline it too. Next thing is the margin of error, which we've already talked about, is E, is the maximum likely amount of error between the sample proportion p hat and the population proportion p. It is also called the maximum error of the estimate and can be found. So there's a couple formulas there we should know, so give those both a star. There's a few notes on here. First one says the confidence interval about the population proportion is of the form p hat plus or minus E. The point estimate p hat is the midpoint of the upper and the lower bounds, which you see up above in the formula. And the third thing says the margin of error E is the difference between the point estimate and the lower bound. So we're going to go ahead and write down a few formulas down here in the space provided. So the first one is that you have a lower bound, and you have your point estimate, which is our p hat, is in between the lower bound and the upper bound. And to go from the point estimate, we are going to add and subtract our margin of error. And so your P, the true proportion for the population, is going to be between p hat plus the margin of error and p hat minus the margin of error. So there's a few different ways to write this. So it's also written as p hat plus or minus E. You'll see that a lot on my Open Math. And then you will also see it written as p hat minus E, comma, p hat plus E in an interval notation. So we have one more formula that we'll write down. Go ahead and scoot over here. Next one that we have is in order to calculate p hat, which is in the middle, so the midpoint between your upper and your lower bound. So I'm going to go and put LB for lower bound plus UB for our upper bound, and we're going to divide by 2. And we've seen this before for midpoints back in chapter 2. So there's an example down below, and it says express the confidence interval using the format of p hat plus or minus E around 3 decimal places. The confidence interval for proportions of red M&Ms is 0.0434 and 0.217, so our true population proportion is between those two. And so we need to come up with our p hat. And so to get our p hat, we are going to add together the lower and the upper bound, which we have, which are given to us. And so adding those together, we have 0.434 plus 0.217 divided by 2, and we get 0.130. The next thing that we need to calculate is E. So in order to calculate our value, our margin of error, we are going to subtract. It's always going to be the larger one, our upper bound, which is 0.217, minus our lower bound, which is 0.0434, and again dividing by 2. And our margin of error works out to being 0.087. So it wants this of the form p hat plus or minus E. So our answer is going to be 0.130 plus or minus E, which is 0.087. The next thing down below, the bottom of the page, give this a star. This is constructing a confidence interval for a population proportion with the TI-8384 calculator. First thing is to compute p-hat, verifying our steps that are written up above that we can actually perform this test. And then I need you guys to check to make sure that you have, if you go to stats, goes to test, it's 1 prop z int. And you're going to enter in your x and your n value, your confidence level, highlight calculate and select enter. This is going to give you a lower limit and an upper limit. And then you need to interpret your results. For you guys, this is talk about. For my open math, she's going to have you fill in some blanks of stuff that you have and that you need to know. So on to the next page, page 4. There is an example at the top that asks for, in a study of the accuracy of fast food drive-through orders, McDonald's had 33 orders that were not accurate among 362 orders observed based on data from the QSR magazine, around 4 decimal places. So the first thing on here says to find the best point estimate. So see if you guys can do that on your own. And then it says identify the margin of error. And we'll talk about that, and we'll finish this problem up together during class time. The next thing I need you guys to look at is there's some formulas down here. These are formulas that you would have to know for your exam. As sample size increases, the result is a narrow confidence interval, and the margin of error decreases. So we have a couple different formulas here. This is figuring out the sample size, so how much data you need to collect. You might have a point estimate. P-hat is known, so maybe you know something from census from 10 years ago, or maybe someone else has done a study that you're doing and they already have some data that you can use to kind of help you out. The second one is when no estimate P-hat is known. So maybe you're the first one doing a study about dog owners and if they're left or right-handed or something along those lines. So we have example down below, and we are going to be looking at these together, but with this formula, first off, it says z alpha over 2 squared, p-hat, and then q-hat. So really quick, q-hat is just 1 minus p-hat. And then E again is our margin of error. Those z alpha over 2 are at the bottom of page, I believe it's page 2. Down here, you will have your z alpha over 2 values. So this is what we'll be looking at in order to calculate those. So again, try reading through it, trying those problems on your own,